or today before this class, but it has not been done, so very soon. Nevertheless. Hello, Legendre.
Hi, Dr. Sajas. Good morning.
Morning. Yeah, this gets delayed here because of the updates. Yeah. And I was a little late also. Is that readable?
No.
No. Every day it's different. We will not work with half words.
Please we make this window bigger and it will be more full. We make this the window bigger.
Oh, but he's saying he cannot. He must be making it bigger, I assume. Awesome. The suggestion is, Niranjan, that are you pinning the video?
Can you say that again, Dr. Sajas?
Do you pin the video that
Yeah.
you do? Right?
Yeah.
I also see the quality difference. Last lecture, I was writing the same size and it was very clear. And here even I have difficulty reading. So
This last time was
last time?
last session.
Oh, last time it was only one. Yeah, okay. Yeah, maybe you're right. Good point. Okay. Well, that's fine. Okay. But yeah, let's do what you do. Okay. And we also have to decide about the dinner. Huh? I did talk to the student or I should say, yeah, old student alumni collaborator now. He's coming on Wednesday and Thursday. Huh?
You won't be on Friday.
You won't be here on Friday. So we'll do something. Okay. I think I'll put the option for you guys to join optional, and Friday we'll discuss. Do you guys have a preference for going somewhere on Friday? Which place do you like? Your experience.
The same place.
Same place? Yeah. The
Yeah.
buffet. Okay. Did you like it?
Yeah. You have any other option? You think?
Oh, don't ask me. No, I think I pick weird places. So let's. Do you know any good place here? How many years have you been here?
This might be bigger.
Okay, so you know.
I don't know these places. There's a Bombay, I love good.
Okay, and
Bond's kitchen, good. Mediterranean place. I like the buffet that you guys were talking about.
do you know what they are talking about?
I think so. So,
Chinquan?
Yes. So that's what they like.
the banana's good, but it's kind of expensive.
Which one?
Banana,
Banana, yeah, banana is a little more expensive. I don't mind it, but I think I'll prefer
yeah.
this one over that. I usually don't get to go in either places because my wife doesn't like Asian cooking. So it's only with these situations I get to go there. So yeah, we can go there, or even Aban kitchen is good. Bombay LA we can skip because there are too many, at least in that regional places. I think they can cook better probably. Yeah. Do you like Indian cuisine?
Yeah.
Okay. That's an option too then. Okay, so but Aban kitchen I like. I do like, yeah. Have you guys been to Aban?
I have.
Yeah, think about it again then. Aban kitchen also could be an option, but let's keep by default we could go to the, what is it? I don't know how to pronounce it.
Chinquan.
Chinquan. Otherwise, we can try Aban kitchen. Yeah. Okay. Okay. We want to Legendre polynomials. Readable? Really not, right?
Uh,
No, right?
I can read, but I'm okay with that, Dr. Sajas. Don't worry about too much.
Better?
Yeah, it's better than before.
It's hard for me to write bigger than this. Okay. What do we mean by polynomials? What's the difference between a polynomial and a function?
Degree.
Degree, yeah. What is that degree mean? I think you're thinking correct. Yeah.
That's the high order terms. That's high order terms. But
Make it more precise. I think you guys are not telling it correct, but make it more precise. Give me an example. Let's say this is a function, but that's fine. It's that this is a polynomial, this is a function. Or every polynomial is a function, but a function is not a polynomial. Something like that.
Have more roots. Polynomials have more roots. No. No.
Now you're thinking in the wrong direction. Earlier you were thinking, yeah, I felt you were in the right direction. So it's relatively simple. Like if you have any function f of x, right? You can write it as a series. This is a series. A1 x plus a2 x squared plus so on. Right? If this is if this goes to infinity, that's a function. Or a function is whether it goes to infinity or not, it doesn't matter. If this is finite, it's a polynomial. Is that clear? If this is a finite, if this truncates, let's say this. Yeah. So this is and j equal to 0 and j x j. If n is less than infinity, then it is a polynomial. That's it. So sine of x is that a function or is that a polynomial? Sine function? No, because this goes to infinity, right? Cosine function goes to infinity. Exponential function goes to infinity. Logarithm function goes to infinity. Those are all transcendental functions. And if it is finite, then it is so if n is let's say 4, then it's a polynomial. If it's a polynomial, as you said, I think Abdullah was pointing out that then if it is a fourth order or the highest power is 4, then that will have 4 roots. And then you can write it as x minus the root, x minus the second root, and so on. But let's not dwell into that too much. Legendre, so polynomials is one thing. Legendre also requires a little pointing out. In your homework, I asked you to do this also. This is sort of interesting. It's kind of a embarrassment also in a sense. If you look up Legendre in Wikipedia or anywhere in principle, there is no picture of Legendre available. Okay, so there is no portrait of Legendre available. But that is only in the last 20 years. Before 20 years, there were a lot of portraits available. Okay, then you say that what happened? The problem was that before 20 years, the picture they were using was a wrong portrait. So there was a mix-up between Legendre, who is a physicist, and a Legendre who was a military personnel. And for 200 years or so, they were using the, maybe not 200, I think somewhere around 1850s, this mix-up happened. And for a long time, the picture that everyone was using was the wrong picture. And then in the modern digital age, they started comparing two pictures. And some students in Paris realized that Legendre name goes to two people. Like the same picture is going to two people, and they realize that, oh, one of them is wrong. And the physicist Legendre doesn't have a picture available for now. So that's sort of a embarrassing in the sense that a wrong picture was being used in literature for more than 100 years or so. But it's also good to know that you should be aware that use the correct picture if you're using it. Yeah, and Legendre was from France. He's during 1800. And remember, everything of whatever we are doing is associated with gravity, 1 over r potential. So we're talking about electric gravitational potential. U is equal to G m1 m2 over r1 minus r2. What's wrong with this? Gravitational potential energy? Minus sign. Okay. So that's a minus sign there. And with this potential, we can calculate the force, Newton's force of gravity, and that's negative gradient of the potential energy. And if you have only one mass, that is usually the sun is the most powerful and Earth is going around, it's very convenient to choose sun to be at the origin, and then R2 is 0, like either R2 or R1, one of them is 0, right? And this becomes 1 over R, and there's a lot of simplicity in that. But if you're talking about more than one masses that is influencing the third mass, then once you have placed one of them at the origin, second one you have to place somewhere else. And the whole symmetry is lost. And once the symmetry is lost, that's where Legendre polynomials comes in. And it becomes harder, and that's what the idea is. So let's first of all see the so we are the idea will be to not choose the origin. Okay, remember the goal is to not keep the mass at the origin, because we are pretending that sun is already occupying the origin, so we want to keep the other planet or other, let's say Jupiter, is not at the origin. and the observation is somewhere else. So the quantities we will be having is, so this is your coordinate system. It is three-dimensional, of course, and this is your R1. It could be anywhere in principle, and R2 is another point. Let's preferably an observation point, maybe. And if you are interested in R1 minus R2, what is this equal to? Let's write that down. Oh, I got out of the. Sorry. Hey. Niranjan, these days I am handling the camera, so feel free to remind me. Okay.
It looks clean now. You can write small if you want.
Oh, so now it has got better.
Yep. I think it is something with the Zoom also.
Yeah, I think the connection, I guess, first. Okay, let's try this. Okay. Better?
Yeah. Yep, that good. That looks good.
So, the context, just for our purposes of having some intuition, is the potential due to gravity, and we don't want to keep one of the objects, one of the masses at the origin, pretending that that is already occupied, or we don't have that choice. Best is, let us say, Sun is occupying here. That's Jupiter. That's your Earth, where the observation is happening. So that's R1 and R2. And the quantity that is coming in is 1 over R1 minus R2. So let's ask what is R1 minus R2 in terms of R1 and R2. If you're working in rectangular coordinates, it is very simple. It is x1 minus x2, the whole square, plus y1 minus y2, the whole square, plus z1 minus z2, the whole square. That's your distance between 2 points in rectangular coordinates. Often we are not interested in working in rectangular coordinates. There are advantages when you're not working in a rectangular coordinate. So let's use a coordinate where it is the magnitude and direction of these vectors that is coming in. And we want to work, let's say, with right here, R1, let's say, is equal to R1 sine theta 1 cosine phi 1, R1 sine theta 1 sine phi 1, and R1 cosine theta 1. That's the coordinates of the components of the vector R1 in terms of spherical polar coordinates associated with the vector R1. Same thing with R2. Be R2 sine theta 2 sine phi 2 sine theta 2. No, did I do this stuff? Yeah. Okay. Two cosine theta 2. Right. And we are interested in the difference between the two. So how will we write this magnitude? You first realize that R1 minus R2 magnitude is equal to the dot product of R1 minus R2. So multiply this 2 times because it's a magnitude, right? So R1 minus R2. And then take a square root for it. So this is the magnitude. So magnitude is a square of the vector. And then take a square root. I take the positive square root. This is the same as magnitude of R1. So this is R1 dotted with R1 plus R2 dotted with R2 minus of the 2 cross terms, that is R1 dotted with R2. R1 dotted with R1 will be just the length, which is R1 itself. And R2 dotted with R2 will be the length R2 itself. So what is more important is R1 dotted with R2. So let's calculate R1 dotted with R2. So that's equal. Multiply the two. So it is R1 and R2 is coming out clearly. First term has cosine theta 1, cosine theta 2. So multiply that. Oh, I didn't mean the first term, last, like the z component has cosine theta 1, cosine theta 2. And the x and y component have sine theta 1, sine theta 2 multiplying together. And the x and y components have cosine of phi 1, cosine of phi 2. That's coming from the x components. And the y component is sine of phi and sine of phi 2. Did I capture that within that? Almost. Yeah. That's the same as R1, R2 times cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2, times cosine of phi 1 minus phi 2. Just to clarify what these angles are in this picture, if I have this to be my z-axis, this is my theta 1. And it doesn't have to be in the, this could be like this. It could be projecting outward from the plane, and this could be right at the tip of the. And that's your theta 2. Theta 1 is outside the plane, theta 2 is in the plane. I'm just saying that it is not in the same plane at all. And just clarify that further. That's your projection. Right, that's x. So this is a third dimension now, and that's your background is it's too much clutter. So that's phi 2, and that's phi 1. Is that clear? Or what I meant here is that so there is an x, there is a z. If you have a vector, so there's a projection always, right? So this is theta, that's phi. This is the respect to x-axis. And that's not y, that is negative y. So each vector has a theta and a phi. Phi is with respect to the axis. Theta is with respect to the z-axis. So these two need not be in the same plane. So that's too much clutter. But either way, that's what it is. So that's too many coordinates though. Like theta 1, theta 2 with first vector, theta 2, phi 2 with the second vector. Not really convenient. And that's not necessarily the best coordinates to use. We do also know that if you have two vectors, so that's your R1, that's your R2. If you have two vectors, they will always be in a plane. Two lines constitute a plane. And this angle is, there's only one angle representing that. Between two lines, there is one angle. I need only one angle. So that's gamma. That's it. What is that angle? That's given in terms of R1 dotted with R2. R1 dotted with R2 is equal to R1 R2 times cosine of gamma, right? Right, so we don't need any of this theta 1, phi 1, theta times phi 2. That's the same as this. R1 dotted with R2 is this. So this is also equal to, if I can write it here, no, I cannot write that. This is equal to R1 R2 cosine gamma. So I learned that cosine gamma is equal to, oh, let me erase this also. So I learned that cosine gamma is cosine theta 1 cosine theta 2 plus sine theta 1 sine theta 2 times cosine of phi 1 minus phi 2. So either work in cosine gamma or work in theta 1, phi 1, theta 2, phi 2. Most of the times, after you've chosen the origin, you still have some freedom to move the axis. You can rotate the axis around. So sometimes you can choose theta 1 and theta 2 in a certain way and get the gamma to be simplified. But in general, you have to keep this. Often, if you're doing a really serious work, you may not have too much choice but to work with these angles. Let's come back to this here. So R1 dotted R1 minus R2, which is our potential, is in terms of, there is this dotted here. So I can write that as R1 square plus R2 square minus of 2 R1 R2 times cosine gamma, where cosine gamma is a short form in principle for this whole structure. Often gamma is sufficient, but at least intuitively you know what gamma is. It's the angle between the vector R1 and R2. But if you have to write it in terms of explicit theta 1 and theta 2, then that's what it is. There is one simplification that comes in. If you choose, this is R1. Sorry, this is Z. Right? So if you have Z axis here and R1 was in that direction itself, R1 is in the direction of Z, R2. But then what is theta 1 equal to? Theta 1 is 0, good, right? And phi 1, then it doesn't mean anything. We can choose it to be 0. If once theta 1 is in the axis, phi 1 practically doesn't exist, so choose it to be 0. Theta 2 is this angle. So theta 2 is not equal to 0, and in general, phi 2 is not equal to 0. But now, what is cosine gamma now? What is gamma, by the way? Theta 2, right? It should be theta 2 itself, but let's see how it comes about. Cosine theta 1 is 0, so it is cosine theta 2. Sine theta 1 is 0, so it is plus 0. It doesn't matter whatever your phi 2 is. This comes out to be 0. That implies that gamma is equal to theta 2. Okay, so if you choose one of the masses to be along the z-axis, then you can get the simplification where gamma shows up. But in general, we don't know what it is. So when we write cosine gamma, it is understood that it is not necessarily on the z-axis. Cosine gamma is just a simplification or a notation to write this whole expression. we are not going to say that it is on the z-axis. Having seen the simplification for this, let us try the following. So this is what we have, right? So let's go back and have more space. So what I want to do is let's talk about 1 over R1 minus R2, and let me not write R1, R minus R prime. I just wrote R1 and R2, but now let me switch over to R minus R prime, and this is nothing but 1 over R squared plus R prime squared minus 2 R prime times cosine gamma, where cosine gamma is a shorthand for, in general, cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2, cosine of phi 1 minus phi 2. As I said, if you're working with gravity, Newton gives this gravitational expression in 17th century, and you're interested in predicting the positions of the planets, then this expression is extremely important. And one of the ideas is, and that's what Legendre tried, let's do a series expansion of this. Like if you have a function, it has a series, right? So we want to write a series expansion for this. And the two parameters will be R and R prime. So if I were to write this as a series expansion, the goal is going to be equal. So I want to write this as a series. And now, what is the series on? I can say that I'm going to expand it out. Let's say, let's do it in 2 steps. So let's pull out our 1 over R. It's not really necessary why you would do that, but it's equal to 1 plus R prime over R squared minus 2 times R prime over R times cosine gamma. Now, what does this depend on? If I don't worry about the R, this depends on R prime minus R and a gamma, that's it. So let me call G of T and X to be equal to 1 over 1 plus T squared minus 2T X. Clearly, I'm using T to be equal to R prime over R. There is a lot of symmetry between R prime and R. Whenever I'm doing a series expansion, it is true only for this less than 1, but I can flip it whenever I want the opposite. Right? If I pull out the R prime, then I get the other one. And you'll see that coming in again and again. And X here is cosine gamma. Notice the notations. We had 2 positions, R1 and R2, in terms of theta 1 and theta 2 and phi 1 and phi 2. And then there was cosine gamma there, and cosine gamma is X. And often this angle is just represented by theta. And T is R and R prime. So the magnitude of the vectors is all in T, and this is equal to X. I said we are going to series expand this, and the goal will be equal. So I want to write this as A0. Don't write this if you, I'm going to erase this in a minute. So this will be A0 plus A1x plus no A1p. A1p plus A2p squared and so on. That's what I want to do. That's Legendre trick that we want to do this series expansion in R prime and R. So if the planet is very far away or very close away, you can make some approximation and not worry about the higher terms, right? You can neglect those terms. So if I, instead of writing A0 and A1, write this as, so this is the Legendre expression, let's call this, that instead of A0, we want to say P0. The second term, we want to call this P1 and leave some space there if you don't want to rewrite it, plus P2 times P squared and so on. This is a function that depends on T and X. Right? So these coefficients must depend on X. Like all the T expansion is contained in the series, T squared, so on. So all this must be X dependent quantities. Okay, so on. This can be written as a summation of L because L is the angular momentum, right? That's where that L shows up. But it has nothing to do with angular momentum here. This is a dummy variable. I'm using L to sum it, but whatever you use in angular momentum, L quantum number like hydrogen atom, that is actually the same L. But in this context, it has nothing to do with hydrogen atom, nothing to do with angular momentum. It's just a dummy variable I'm using to sum things together. This is P L X and P raised to L. Okay. Now let's define a few things. This is called the Legendre polynomial. Legendre polynomial of order L. If I write PL of X as a series, is it a polynomial or a function? It's not obvious, but since it is saying it's a polynomial, it means that it will truncate. It won't go all the way to infinity. So that's why it's a polynomial. T is an infinite. It is going from L equal to 1, 0. Oh, I didn't write that. L equal to 0 to infinity. As a function of T, this is an actual function. It's not a polynomial. It will go forever unless there is some special reasons why it will truncate itself. But in general, this goes all the way to infinity. This, since this is generating the Legendre polynomial, this is a way to define it. This is called the generating function. Of Legendre polynomial. That's the definition, but I have not done anything in principle. I gave you the gravitation potential and said there is some simplification if you do it, or it's useful if you can do this. But I never told you what PLS is. And you have to derive it, right? Once, if you were Legendre, this is the first time you're doing it, and you know that if T, which is R and R prime, is small, you can expand it. If you're really close to the planet, then higher orders can be neglected. You will be interested in calculating P0, P1, and so on. So we have to calculate it. So we'll pretend we are Legendre and really calculate it. Of course, you can give it to a student, if not a computer, right? And ask them to calculate it. But let's see how this shows up. Okay. So, And it is literally, I mean, actually, literally done. I mean, you have to do that in a rigorous way. That's okay. So, let's begin by saying that gamma is 0, right? Let simplify, right? Let gamma be equal to 0. Then what is x equal to? X is equal to 1, right? Yes, x is equal to 1. Because x is the sign of gamma, which is the sign of 0. That's it. What is 1 over r minus r prime then? Is equal to, here it is 1 over r, and let me not even say, yeah, 1 minus r. What do I do? Okay.
Just R1 is 1 prime.
The length, right? Because both are in the same direction. Very good. So now let me draw this. So this is R, and R2 is in the same direction. This is R1, and R2 is in the same direction. Oops. Well, R2, that's R2. And R1 is smaller than that. Right, they are in the same direction, so it is the length alone that decides what this. So it is basically R minus how is it? It's built in 2 steps. It might be more illustrative to do this. So this is R square plus R prime square minus 2 R prime cosine of 0. So that's equal to 1 over r square plus r prime square minus 2 r prime, which is nothing but 1 over magnitude, this is square, right? R minus r prime square. This and a small. So what is this equal to? R minus r prime? Magnitude, right? So it has to be magnitude. So let's pick this magnitude. Let's be picky about this. This is equal to 1 over r minus r prime if r is greater than r prime, so r prime is less than r. And it is equal to 1 over r prime minus r if r is less than r prime. So whenever you're working with Legendre polynomials, you will often see expression involving less and greater. So this will be returned as, so this is too much writing, right? So you get lazy for every time I had to write 2 conditions. Right? So you come up with a notation that this is 1 over r greater minus r less. Okay. You probably already used these notations in electromagnetism. So r greater here means maximum or larger or maximum, right? No, not maximum, larger, greater of r and r prime. And r less is equal to lesser of r and r prime. Like what are the smaller? Whichever one is smaller, that's what we call less, and the other is larger. I'm interested in the series expansion for this. Right? I would like to get this P0, P1 for this. So let's do this. So this is equal to 1 over r greater over 1 minus or less over or greater. We're doing simple things, that is, but see the motivation behind the whole thing. And that's equal to, now I can write the series expansion for this. What is the series expansion for 1 over 1 minus x? 1 over 1 minus x, series expansion? Anyone? Coefficients? So it is, how you do this is,
You can write 1 minus x to minus 1, and then it's 0.
yeah, so this is the easy one to remember, so that's why it's just square, but you were saying, yeah, so how you do this is 1 minus x raised to n, right? Is that what you were suggesting? Yeah. So this is equal to 1 plus n times x plus n times n minus 1 over 2 factorial times x squared, and it keeps going forever. Right? If it's an integer, let's say 1 over x squared, then somewhere it will stop because it is equal to 0. Right? If n was equal to 2, this term will go to 0, and so on. Okay. Is that fair? So this is equal to 1 plus r less over r greater plus r less over r greater squared plus 1. Okay. That was a simple exercise, but now if I ask you, what is P01 equal to? What is P01? 1, right? The first term in this expansion is 1. X is equal to 1 because I set gamma equal to 0. Right? So I know now that P01 is equal to 1. P11 is equal to 1. In fact, I know all Legendre polynomials now. PL for any L is equal to 1. That's used as a normalization. That is like the way I built it. It turned out that this will always be equal to 1. So PL at, so often you also say PL, the sign of gamma, or the sign of 0 now, right? The sign of 0 is equal to 1. The sign of 0 is 1. So that's equal to 1. Is that clear? But we are interested in the complete Legendre polynomials, right? So complete Legendre polynomials, how we do. So this is, there was a lot of simplification here. Do this explicitly without setting gamma equal to 0. Do the whole series expansion and read out each one of them. And it gets tedious very quickly. And we will do till 2 here and then try to see some pattern in this. Any questions at this stage? And once you have those polynomials, we will have to talk about orthogonality of it, what's the differential equation satisfied by these functions, and what is the completeness relation. Usually completeness, orthogonality, and differential equation, those are the fundamental things that you need to know about any special function. Okay, again, any questions, comments? Okay, so again, we have the generating function t comma x equal to 1 over 1 plus t squared 2px. And if our goal is to expand this as a series, and this is going from L equal to 0 to infinity, you get PL x times t equals to L. So the idea is to expand this out as a series in T. So treat this as one whole term, so this is equal to, and I just now told how we see it expand. So you have 1 over, let's say 1 plus. No, what I wrote earlier, did I say that correct? I think this is how you expand it. 1 plus x raised to n. I think I wrote 1 over, right? This is equal to 1 plus n times x plus n times n minus 1 over 2 factorial by x squared, and same, keep going. If n was equal to 2, it is trivial. You will get n times n minus 1 times n minus 2, that goes to 0, and every other term will be equal to 0. But this is useful when it is fractional. If it is not an integer, then you see that it will go forever. Right? That's but this is always works. This is the binomial expansion given by Newton. Newton was the one to realize this, and very useful expression. We learned it as a binomial here. So here, let's treat this whole thing as one quantity, and this is the same as 1. Let me write this as 1 plus t squared minus 2px raised to minus half. So this will be equal to 1, and I have minus half, that's here n, times t squared minus 2px. The next term is plus minus half. And minus half minus 1. And then there is a 2 factorial, 1 over 2 factorial. And I have t squared minus 2x raised to square. And next one will be, I think we may not need it, but let's see. Okay, so minus 1 by 2. So there is a minus sign for sure. Then I have 1 by 2, 3 by 2, 5 by 2, and 1 over 3 factorial. Try to write this in single. So t squared minus q and so on. So something expanded, and our goal is to collect terms, right? I want to collect t raised to 1, t raised to 2, t raised to 3. I will do it for 3 or 2 terms, 0, 1, and 2, and rest of it. I'll give a pattern which may not be obvious. That also we can derive another place. So this is 1 minus 1 by 2 t squared plus x times t. I've done this 2, so it's plus. This is plus 1 by 2, 3 by 2, and 1 by 2. So it's 3 by 8 plus 2 by 8 times t raised to 4 plus 4x squared minus 4x. Let me know that is if you see an immediate mistake. That's 4, 8. Let me know if guys you see a mistake. Okay, we are collecting terms of 1, 2, and so on. This is 1, and let's collect the t. So this is 1 plus g x. I have this term here. So it's minus 3 by 2 x. I'm already making mistakes. Now let's make it. There is no key in this. This is not. Do you guys remember here? P0. Yeah, P1 is x. So this should come out x. So this. Did I do this right? Minus 1 by 2. Hmm?
Four P squared X. So second, the first time,
This one?
or the next one, the next
This one? Oh, what is this?
4P squared X.
Oh, yeah, 4p squared x. Yeah, okay, so that's not important. Okay, that helps. Then am I good? Yeah, that's good. Okay, that's good. Did I mess up? Is this correct? Okay, yeah. Let me know if that is. So I haven't done this thing. So I'm doing. Okay. And this is also then. Part of the line. Oh,
Did we forget to put t?
yes, please, Narendra.
Below the generating function, second line,
Yeah,
that line, within the parentheses, we have t squared minus 2tx.
Yes.
Squared minus 2T.
Yeah, that's, if you come to the next term, are we missing that t squared minus 2tx? Maybe I'm wrong.
oh, so here there should be a key, you're saying.
Yeah.
Oh, yeah. Okay. Thank you. Okay, so that messes up everything. Okay, thank you. Okay, my bad. Come. We'll be back. Okay, so now do this again. Thank you. Okay, so this is t raised to 4. And yeah, this helps. Okay. So this is plus 4t squared x squared, 4t squared x squared, and now this is minus 4t cubed x. I'm going to do this again. So t raised to 6 minus 3 times that is t raised to 4, t raised to 5 x. So it's 3 times t squared 2 x 4, 5, 6 x. Okay. Plus you have 3 times t squared 2 x the whole square. 4, 3, 12 t raised to 4 and x squared. finally minus 8 into 16. Right? Okay, so hopefully it's better this time. Thanks, everyone. Okay, one, and we did not, so now we are writing p, right? So we use plus. There is no other place that is a coefficient of one, and that is p. There is only x, I suppose. There's only one term with t. Next is t squared. And there is a minus half. That's this term, t squared, that is a 3 by 2 plus 3 by 2 squared. And t squared, nothing else. The next one is t cubed. What is t cubed? Is minus 2 by 2. That's minus plus 5 by 2. And so on. P raised to 4, we will need to do more terms. We don't have the complete so. And immediately we read out that now this is complete, not just 1. So P0x is equal to 1. P1 x is equal to x itself. P2x is equal to 3 by 2 x squared minus 1 by 2. And P3 of x is equal to 5 by 2 x cubed minus 3 by 2 x. Let me check. 5 by 2 x cubed. Yeah, this is all right. If I were to plot this in a very straightforward manner, so this is x, and this is PL of x. Notice x goes only from 0 to 1. Theta is theta can go only from 0 to 5, right? 0 to 5, so this can go from minus 1 plus 1, yes, right? Minus 1 to plus 1. Easiest is P0. That's P0x. Second one is 3 by 2 minus when x is equal to 0, it's minus half. This is plus 1, minus 1, so minus half, and then it grows as an x squared. And right when x is equal to 1, this is just equal to 1. So this is actually like this. It's a parabola which meets that at x equal to 1. You don't go beyond that because x is not valid for that. When you do P, so this is P1, no, this is P2 actually, there is P1. P1 is just x, right? That's straightforward. It's like this. This is P1 x, and P3 of x starts at x equal to 0. When x is small, then it is minus 3 by 2. This, so the slope is like this. And when x is equal to 1, it is again 1. So I think it goes like this. Goes like this. Quiz. Plot, okay? Plot P13 of x. Okay. Use a software. Don't try to calculate the 13th order. That's too much work. Okay. But try to plot it using a computer. Use plot using compute. Okay. And I just randomly pick P13 or your favorite number of X, but something non-trivial. That's all. It's and next time we will do differential equation and maybe recurrence relation. And in your homework, probably there will be a possibility. One of these things I'll put it in the homework. The other will be in the class. Thank you. Oh, give me 1 more minute. Sorry. I think I was wanting to do that. I don't know why I forgot. Yes, the final exam. That's an important announcement I want to make. Some of you guys are struggling on the border, right? So here, I don't want to take all the responsibility on me to decide your grades. So here is what there will be 5 questions in the exam. 3 will be take home and 2 will be in class. So and 3 take home, you can take help from anyone, you can take help from me. Okay, so you should be able to hopefully try to score all the points from there. So final exam, there will be 5 questions, 3 is take home, you can take help from anyone, 2 will be in class. Okay, and the total you need to get in the final exam, this is for those who are struggling. The total you should get from what I understand, if you get a 75% in the final exam, okay, everyone in this class should get an A. For those who have already scored a lot, then probably you don't need to get 75% in the final exam. Okay, but 75% in the final exam, with the fact that 3 of the questions is take home. So the 2 questions matter a lot. So if you mess up, then it's not me. Okay, then it's you earning that. So that's clear. Okay, so it's up to you guys. So if you get 75%, then I will give you the A. Otherwise, then I not miss. Okay. Thank you. Sorry, I wanted to tell that more clearly earlier. Thank you. Okay.
Thank you, Dr. Sajis.
Yeah. Oh, yeah. Thank you. This is homework for the dude. I didn't